Next we see some problems involving theory. Let's see this number 68. The temperature in Fahrenheit in Fairbanks, Alaska on day X of a typical 365 day is given by this general sine curve. Y equals 37 sine 2 pi divided by 365 times x minus 110 plus 25. So y is the temperature in degrees Fahrenheit and x is the day of a typical 365 day year. There are two parts to this problem. This is part A. On what day is the temperature increasing the fastest? So you understand what you have to do. You have to differentiate this with respect to x. dy dx is what you have to find. And then you have to say when that dy dx is the largest, because that will be the day when the temperature is increasing the fastest. So in the solution we find dy dx, and of course we have to apply the chain rule for differentiating, because inside the sign you have this inner room. So if you differentiate, this one of course is going to give you only 0 because it's constant, and by the constant multiple rule 37 anyway is going to stay outside. Now when you differentiate the outer sine room, you get cosine of the inner room, and then you have to multiply that with the derivative of the inner room. Now the inner room is this, where already there is a constant outside, so that will come this one 2 pi divided by 365, and differentiating x minus 101 you will get 1. So that is why you only have this, and when you do the multiplication this is what you get, 74 pi divided by 365 times cosine of this. Now you have to say when this is the largest. So obviously this value involving a cosine term would be maximum when this cosine is 1. So we write this rate of change of temperature is maximum when the cosine term is 1, and that happens only when this argument inside the cosine is 0, which in turn corresponds to the x value, x equal to 101. So this means that on day 101 the temperature is increasing the fastest. This does not mean that the temperature is the highest. It means that the temperature is increasing the fastest. The rate is the maximum. And next we have part B, about how many degrees per day is the temperature increasing when it is increasing the fastest. That means we have to find the fastest rate, or in other words we have to find the value of that derivative when x is equal to 101. So we calculate the derivative at that point x equal to 101, and of course we have only this, the adjacent cosine term becomes 1, and when you do the calculation on your calculator, roughly this is the answer that you get. 0.64 degrees Fahrenheit per day is the rate at which temperature increases on day 101, and this is the fastest rate of increase. Next we have this number 70 involving a falling body. Suppose the velocity of a falling body is given by this expression, k times square root of s meter per second, that's the velocity, v equals this, where k is a constant. At the instant the body has fallen s meters from its starting point, we have to show that the body's acceleration then is constant. So we just start straight away with the acceleration, which is the rate of change of velocity with respect to time of course, and this is your velocity, k times square root of s, where s is the distance the body has fallen, and k is first of all constant, so it comes out of the differentiation process by the constant multiple rule. Now you are looking at the derivative of square root of s. Note that the distance the body has fallen, that is s itself, is a function of time. So that means this is a composite function of square root function and that function s. So you have to apply the chain rule to do the differentiation. First of all you differentiate the outer square root room. Doing so you get 1 divided by 2 times root s. You already know this derivative, and then you multiply that with the derivative of the inner room, which is s. That, however, is nothing but velocity, rate of change of distance with respect to time, or rather rate of change of position with respect to time. But velocity is k root s. So you can see that square root of s is getting cancelled, and that leaves you with k square divided by 2, because k is constant. So this acceleration is itself constant. K square divided by 2 meter per second squared is the constant acceleration with which the body is falling. Next, number 72. A particle moves along the x-axis with this velocity. Velocity, of course, is dx dt, and it is given by some function f of x. Then we have to show that the particle's acceleration is the derivative of f times f prime of x times f of x. So we start the solution by considering the acceleration. If velocity is dx dt, then the acceleration is the second derivative. That is d dt of this thing, which is f of x. Now in f of x, x itself is a function of time. So in doing this differentiation, you have to apply the chain rule. So first you differentiate the outer room and you get f prime of x, and then multiply that with the derivative of the inner room. Inner room is x, so dx dt. But dx dt is f of x, so that's how you have your acceleration. The next one, number 74, tests our understanding of the chain rule. You consider these two functions f and g. F of x is the ordinary square function and g of x is the absolute value function. And then you consider these two composites. F composition g you can see easily is x square, and g composition f is also x square. And we know that the square function, so actually we just get back f, nothing else. So the square function is known to be differentiable at x equal to 0. That means viewed as these two composites, the square function, that means these two composite functions, both are differentiable at x equal to 0. Even though g itself is not differentiable at x equal to 0, which is also something we already know. There, if you think of the graph of g, there is a sharp corner at x equal to 0. So the graph has no tangent at that point. G is not differentiable. But because composite functions are involved, so we can apply the chain rule to find the derivatives of the composite functions. They are actually the same function, but we can apply the chain rule. But if one of the functions is not differentiable, the other one, however, is differentiable, and we are getting the fact that the composites are differentiable, so is something wrong? Has this thing contradicted the chain rule? We have to explain. And the answer is that no, the chain rule is not contradicted here, because we cannot apply the chain rule here in the first place, and that is because g is not differentiable at 0. So this is the formal solution, the formal answer. But let's look at it a bit more closely, exactly what is going on. So in order to understand what goes wrong if we try to apply the chain rule, we again consider the functions f and g. But because we are talking about the chain rule, so we write f slightly differently. Instead of writing f of x equal to x square, we write f of u equal to u square. Same thing, whether you name the independent variable x or u, it does not ultimately change anything. It remains the square function. But now u is being viewed as this function of x, g of x, which is mod x. So f is a function of u and u is a function of x. So what does the chain rule say? The chain rule says that if two conditions are satisfied, then it gives us something. And those two conditions are these. First of all, this function u, which is a function of x, should have a derivative at say x equal to 0. If this exists, which actually is, it does not exist. So this is where things stop in fact. But anyway, let's see the other condition also. and if the derivative of f with respect to u at g of 0 also exists, then the derivative of f with respect to x exists, and it is equal to, at x equal to 0, its value is equal to the product of these two derivatives. That is the chain rule. If these things are true, then that other thing is true. But the thing stops at if itself. So that is why the chain rule is not even applicable here. So obviously it hasn't been contradicted. And you can see the other composite function also, treating g as a function of u and f as a function of x. So I leave that to you. Next we have number 76, and in this one also two functions are given. U is a function of x and the function is g. It's given that it is differentiable at x equal to -5, and y is the function of u and the function is f, and this one is also differentiable but at u equal to g of -5, and it is given that the derivative of the composite f composition g at -5 is negative. What, if anything, can be said about the values of these two derivatives, the derivative of g at -5 and the derivative of f at g of -5? So we start the solution by applying the chain rule straight away. The derivative of the composite at -5 is equal to the derivative of f at g of -5 times the derivative of g at -5. Never get confused in writing this. Always remember the outer room, inner room. That's it. First you differentiate the outer room f, keeping the inner room g of -5 intact, then multiply that with the derivative of the inner room at that -5. That's it. Now it's given that the derivative of the composite is negative. So this means that the product of these two real numbers is negative. So one of them will be positive and the other will be negative. Either this f prime of g of -5, f prime at g of -5 is positive and this g prime at -5 is negative, or the other possibility is true. So we can say only this much about the values of these two derivatives. And finally we have this number 78. Here, using the chain rule, we have to show that the power rule, our usual power rule for differentiation, holds for this power of x, x to the power 3 over 4, which we can also write as this, square root of x times square root of x. You can see, you can go through the calculation, and using your familiar rules of exponents, you can see that this is actually equal to this. So we start the differentiation of x to the power 3 over 4, which is the derivative of this. Now here first you apply the chain rule. Here you have an inner room which is x root x, and the outer room is the square root room. So first you differentiate the square root room, you get 1 divided by 2 times the square root room, keeping the inner room x root x intact, and then you multiply that with the derivative of the inner room. Now in the next step, here you have to apply the product rule for differentiation, and then let's see what happens. So in the next step, before applying the product rule here, we simplify this. Simplify this means in place of this we write x to the power 3 over 4, and then we apply the product rule. Differentiating x, we would get 1. So one of the terms will be root x, plus differentiating root x, we will get 1 divided by 2 root x. So the other term will be x divided by 2 root x. So this part which is outside becomes this 1 over 2 times x to the power -3 over 4, because it was originally in the denominator. Now what will you get if you do the calculation here? Taking 2 root x as your common denominator, you multiply this by 2 root x. So that way you get 2x. 2x plus x is 3x. So that way you get 3x divided by 2 root x. Now this 2 and this 2 give you 4. So 3 divided by 4 times. Here you have 1x. So because of that you have 1 minus 3 over 4, and this square root in the denominator gives you this minus 1 over 2 exponent. Now if you do the calculation, you get minus 1 over 4, which can also be written as 3 over 4 minus 1. So are you not getting the power rule with this exponent 3 over 4? 3 over 4 here, it comes down, and then you subtract 1 from the exponent. So that way you have your power rule again true here, even for a rational number exponent which is not an integer. And with this, let me just end this set of exercises. The other ones which we have after this, they involve using some kind of graphing facility. Desmos, of course, you can use. So please go through them. And in the next calculus video, we can start the next section, which involves implicit differentiation and rational exponent. So there we will see in general that this power rule is true for any rational exponent.